Welcome everyone. Throughout the previous projects, we've created CUDA programs to add two vectors, but those vectors were of a small scale. In today's video, I am going to cover the same application, the vector addition application, focusing on vectors of much larger sizes. This task won't be as straightforward as our previous projects. It's going to be more complex, and we are likely to encounter several challenges. However, I'll identify each challenge or each issue as we come across it, and I'll offer the corresponding solution. In our last project, the vectors were sized at 2048 elements. For that project, we assigned two blocks in which each containing 1024 threads. In today's video, I'll increase the vector size to more than 400 million elements. So all we need to do now is to take a look at the code. As we see, the vector size will be 1024 multiplied by 432 multiplied by 1024. And this is more than 400 million elements. To process all these elements, we must adjust the main configuration in the application, the number of blocks and the threads per block. So let's go to the instruction of launching the kernel. Here in this instruction, I'm going to use 1024 threads per block. This represents the maximum limit of our GPU. And for the grid size, the second configuration, or the count of blocks, I'm going to use 1024 multiplied by 432 blocks. And the multiplication of these two configurations should be equal to the total number of elements in each vector. Everything else in this code is similar to the previous projects, so we are not going to edit anything else. Let's now compile and run. The execution of this application is going to take some time because we are working on large vector sizes. As we see, everything is normal and some of the results are displayed as shown, and you can choose any row here and test if a plus b is equal to the value of c. But anyway, we don't have problem here, even for the compilation or for running the application. We do not have compilation error or runtime error, okay? The error or the problem or the challenge shows up when we duplicate the vector sizes. So let's come to the vector size and remove the 432 and replace it with 1024. And now for each vector, we have more than 1 billion elements. Let's now compile, and as we see, we do not have any compilation error at all. Let's now run the application. As shown, the code fails to run correctly, and we know that because no result of this for loop here in the code is displayed on the output terminal. Additionally, you can notice that an error message appears on the terminal. Here in this code, if it is 0, then there is no error. If it is a number, then we have an error or we have a runtime error, because as we said, we do not have a compilation error in this application. Now, my question is, why do we have an error in this application now? I need you to think about this question. What are the possible causes for this error? Alright, let me provide you with the solution. There are numerous strategies for debugging the code to find the exact issue. In scenario like this, one of the most effective debugging techniques involves the use of the printf function. You put many printf instructions in different locations in the application, and then you run the application, use the output on the terminal to find the line that has the issue. So let's start writing the first printf here at the beginning. So let's write printf /n let's write, for example, hello 00/n. Copy this instruction in different locations, but let's do a small change here, 01 and 02. Now we have printfs in many locations. Why do we need to put printf instruction in different locations? Because we need to identify the line where we have the error. This is a challenge, okay? Because you do not have an error like this. If we remove the semicolon from here and then compile, the compiler will let you know what is exactly the problem. When you click here, you can see that it is before this line. So we know that there is a problem in the semicolon here. So we can write it and then compile. But in our situation, we have a runtime error, not a compilation error. As you see, it is succeeded, so there is no compilation error. Now let's run to check which of these printfs will print output on the terminal. 0001, but 02 didn't print anything. So now we know that the error exists before line 42, before this printf, okay? So we saw hello 00. This means that there is no error before this printf. And we saw also on the terminal 01, as we see here. So there is no error when we are allocating space for the vectors on the GPU, not the CPU, because we are using here CUDA malloc. And then we didn't see hello 02. So we know that we have a problem in these instructions here. So my question here is, what is the problem in these three instructions? To understand this, let me take you here through my available space in the RAM or the memory. As we see, we are using now around 10 gigabytes. However, the total amount of the global memory in my computer or the RAM of my computer is 16. So we have around 5 or 6 gigabytes available to run any other application. Let's go back here and see when we run this application, what is going to happen, okay? We have three vectors, so we will allocate a space for vector A, and then initialize this vector, allocate for B, initialize the vector, and then allocate for C. And we do not need to initialize C because this is where we are going to store the result. So let's run, and while we are running, let's take a look here on what is happening to the memory, okay? Look at the value and the shape. Did we click run? No, we didn't click run. Okay, so let's now see what is going to happen. Oh, it didn't execute, right? Because as I said, the problem still exists. What we need to do is to come here and, for example, remove this and replace it with 432. Run again and look at here. So printf hello 0001. So now we are allocating space for vector A on my CPU memory. On my RAM of the laptop. Once we finish allocating for vector A, initialize it, then we are going to allocate a space for vector B. And you can see that the space is around 200 gigabytes or more. As you see, now we are using more than 300 gigabytes. And there is still a small space here around 2 or 3 gigabytes. Let's see. So it works fine and it prints the results. However, the results are not correct. 38, for example, 38 plus 2 should be like 40, but we do not have 40. And the reason for that, when you change the vector size, you should change the configuration of the application, okay? So let's come here and change the configuration. We should replace this one by 432. But I'm not going to do this now. I'm just telling you the problem. Okay, so to solve this problem, all we need to do is to divide our vectors into small pieces. So here, this is 1024. This is where the problem shows up. And this is a very large size. And you can now calculate the total size in gigabytes. All you need to do is to copy this. So multiply it by 1024 by 1024. This is the total number of bytes for each vector. The total number of elements, not bytes, okay? I'm going to multiply by 4 to get the total number of bytes because each element consists of 4 bytes. This is an integer element, okay? Now, this is the total number of bytes. I'm going to divide it by 1024 to get the value in kilobytes. And then we'll divide again to get the value in megabytes. Divide again to get the value in gigabytes. So each vector will be 4 gigabytes. And that's why this is not enough to store 3 vectors. To store 3 vectors, we need 12 gigabytes, which is not available in my computer. Now the solution is to divide each vector into small pieces. How many pieces do we need to use in our application depends on the available memory you have. So you have around like 4 or 5 gigabytes. So the small pieces of each vector should be less than this amount of storage. So let's say, for example, replace this value with 512. That means we are going to divide each vector into 2 pieces, because if you divide this by this, we are going to take 2 pieces, and each piece called chunk. So we are going to use chunk sizes here to divide each vector into small pieces. And if this is still large to be stored in the available space here, all you need to do is to make it smaller. So for example, 128. And then you have each vector is divided into 8 pieces. And 8 pieces because if you divide 1024 over 128, this is going to be 8. Let's do this to make sure that we are correct. 1024 over 182, this is 8. So each vector is going to be divided into 8 pieces. And then all you need to do is to take the first piece of A, the first piece of B, or the first chunk of A and B, add them, and put the result in C. Once you finishes, remove the allocation of the memory, free the memory from these values, and then go to the second piece of the vectors. Once you finish the second piece, go to the third piece, and so on. I have the code, so I'm going to copy the code from here and put it here and then explain it. So we have here the total size of each vector. I'm going to edit it again. So this is the total size, and then I'm going to divide it into 8 pieces or 8 chunks, chunk size. This is the size of each chunk. The block size is 1024 threads per block, and this is already explained many times in the previous projects. Then we have here the kernel. There is no change in the kernel, GPU kernel. There is no change in this function here that initializes the vectors, and also there is no change here except that we are using chunk A, chunk B, chunk C instead of A and B and C. Okay, because we need smaller sizes. We do not need to store values or allocate space for the whole vector. Now here we are allocating the memory space for the GPU without any problem because the GPU has enough memory. And here we are allocating space, but for the first chunk from the vector, not for the whole vector. As you see, chunk A, and we are using malloc with the chunk size bytes, not the total size of each vector. Now we need to initialize each of these chunks, the first chunk of A and the first chunk of B, and then sends these values to the GPU by using the CUDA mem copy, okay, and then execute the kernel that adds the two vector on this chunk only. We didn't execute, we are not executing now on the whole vector, and then copy the result back to the chunk C. Now you can take the chunk C and send it anywhere. You can print it, you can give it to another function, you can do it whatever you want to do. But this is just a small example. Now we finished the first part of each vector. We need to go to the second part. That's why we need to use for loop. This for loop is going to iterate over the 8 pieces, the 8 chunks. So as you see here, we iterate over the second chunk, the third chunk, and so on until we finish the vector addition on all pieces of all 3 vectors. Let's now compile. As you see, succeeded, so let's run. Offset 0, I am printing offset here to show you the offset of the start of each chunk. The first chunk starts from 0. The second chunk, let's see where is exactly it is going to start. Yeah, it starts at this number, and this number should be equal to the chunk size. The chunk size here. Chunk 3, and I think that now you know how many offsets are going to be printed on the terminal. We should see 8 chunks, okay? I should have moved the printf of the C values after the CUDA mem copy for the C values here to print some of them. At least we should have printed like 5 elements at least for each iteration. But anyway, you can do this. I'm going to print some elements, 100 elements, but from the last chunk, okay? Because this is the end of this for loop here. So 1, 2, 3, 4, 5, 6. We still have 2 chunks. Seven. I also want you to look at the memory here. Now we are using only 11 gigabytes because we allocated only a space for 3 chunks, not 3 vectors. And when we finish, you will see the effect of the deallocation or freeing the vector A and P and C from the memory on the available space here. Let's see. Do you see the difference? So it goes back again to 9.4 gigabytes. And the results are correct. As you see, 13 plus 77 is equal to 90 and so on. That's the first challenge that we are discussing in this video.